So yeah, just remember when and where the final is going to be. It's going to be here on Monday at 3. And yeah, just be a review. Remember to turn in anything late. If you didn't complete an assignment on time, you still get half credit if you submit it late by the end of this week. So Friday at 11:59 p.m. you can turn it in late. And then on Monday, on the final day, you'll just come in to the class and this week 18 module will be, oh shoot, are you able to see any of this? Uh, that's confusing. Sorry if I didn't do that right. But for sure now you can see it. You are able to, you'll come in, you'll see this module, and you'll click the final, just like that. So yeah, that's what we're doing. And I think that's all that I wanted to say before we begin the review. Are we good? Any last logistical questions or anything before we get started? All right, let's do it. So, for old time's sake, what we talked about before we went over midterm 1 stuff, like table stuff, we talked about testing hypotheses, we talked about doing that in a different way with permutation tests, like testing hypotheses with sample proportions, testing it with a permutation test, like shuffling around, making our own shelves, like if the label really didn't matter, then surely we'd see a shelf 2 randomly generated that was just a sugar and we did not. So that was interesting. And so next I want to go on to the idea of a bootstrap and confidence intervals. That gives us both of those all at once. So I want to go and use the Titanic to do that. So let's do, so remember, the idea of a bootstrap is you got one good sample. You got one really nice sample from your population, and you are you would really like to know how good of a sample that is, or you assume it was a good sample. You would really like to have some other samples to see how the values might vary. Because if you took the average value from your sample, this is your one good sample, all these data points. If you calculate an average, like, I don't know, maybe the average is here or something. Where's a number line when you need one? So say like this is your average for that sample. But the idea is if you took another sample, you maybe would have changed, like, let's say we want to know the age of everybody in the US or something. If you took a sample of people, you get a certain average age. But if you took another sample, you'd probably you'd get a different jumble of people's ages. Maybe you have a younger person now and that excluded another older person. And so like if you took another sample, your average might, of the same number of people, your average might be over here, or might be over here. The idea is, if you could take another sample, you get new values. So how can we see how a statistic would vary given another sample? And that's kind of what bootstrapping does for you. It lets you get another sample on the fly where you sample from your original sample. You sample as many rows as you have, but you do it with replacement this time. You're allowed to duplicate things. And so that lets you get another, like maybe a better picture of what the population might look like, because maybe there are really like 2 of those younger people that you just drew from, or there's more older people, and so you'll draw an older person twice or something if you're doing age stuff. So that will allow you to get a bunch of different samples, and you can see, like, you can do a confidence interval by taking, all right, I want what's the middle 95% of all of those ages that I find when I take the average age of a bootstrapped sample. So just a bootstrap, the idea is like you're making a sample from an existing sample, and that lets you get a clearer picture of what your population might look like and how it varies. So yeah, any questions about that before I show you code? It's kind of the idea, right? So that's all in other places too. So you can always go back to the book. You can always go back to the lecture slides and example. What's it called? All the assignments as well, right? So yeah, let's do Titanic things. So let's say we would really like a 95% confidence interval for the average passenger age. And I need to set this up a little bit more, though, because we know the exact average passenger age for the Titanic, right? We have a list where our Titanic data set has everybody who was on the Titanic. Like, we could actually get the real average passenger age. That's easy for us. But let's pretend like we are, like, the Titanic just sunk. what year was that? 19 something, right? Table 1909, some early time. Let's say that like we're on a lifeboat and the lifeboat can only hold like 100 people. We'd like to know from that sample of people that we have available to us, like what is a good idea for the average passenger age. So let's do so let's read this table, and then also some of the ages in the Titanic data set are undefined. They're nans and stuff. So I'll just say dot where age, where the age values are above or equal to 0, because you had babies on the Titanic. So at least 0, so not undefined like a nan is, and not a number is. So that will be my version of the table with just people that actually have ages. Okay? So we can get the real age, but let's pretend the Titanic just sunk. We don't have all the data. We have like one page of data. We have the first page of the passenger sheet or something, and we have the ages of each of those passengers, but we don't have everybody on the Titanic. We can glean some information from that still, right? So bootstrapping is all about you got to sample, right? This Titanic data set is a census. I'm going to prove to you that bootstrapping works again, right? That's what we did the first time. So let's say we would like to, let's say that all we've got is, we've got a page of 100 passengers only, not all 714. All right, so let's take, just for fun, let's pretend we only had a size 100 sample. Pretend we only have a size 100 sample, and that's all we have, size 100 sample, and that's all we have. And that's it, okay? So sample equals, so just for fun, I'm going to randomly generate a sample of Titanic passengers. So we're going to pretend like we only had the first page of the sheet of people who signed up to go on the Titanic, and we have their ages. Okay, Titanic.sample, and I want 100 people, and I want with replacement equals false. Come on. Why is this not working? With replacement. We're going to find out what happens here. So like that's my sample, and with replacement equals false means I'm not going to duplicate people. Like I'm just going to have give me actual people on the Titanic. Don't turn Mrs. Nasser into 2 Mrs. Nassers. Keep just one, please, if you take her. So do that, and then once I have that sample, let's pretend that's all we get. Oh, I spelled it wrong. That's why. Titanic. There we go. There's my sample. It's got 100 things in it, and it's 100 different people on the Titanic. Let's pretend that's all we got. We were like, those were the people on the lifeboat or something, or the people that they knew about on the lifeboat. Like I've got 100 people only, and I want to infer something about everybody on the Titanic right now. All right, that's my goal. And so this is one good sample. It is random, perfectly random, probably better than they could have done, and it should be representative then of my population, and so I can bootstrap it and get some good knowledge. All right, so what we will do is, to make a bootstrap, we're going to sample again from our sample. We're going to say sample.sample. It's a little weird like that, but when you do that, you say sample.sample. The default is the same size as the sample's size, so it's like you said 100 again, because there are 100 things in the sample table, and it's with replacement equals true. True. So those are the defaults. You don't have to say either of those. It's just like it's the same size with replacement equals true is what's happening. All right. So that's what it means to take a bootstrap. That's a resample. So if you do that, you got a new, slightly maybe better picture, different picture of your population, but still similar. Like that's how your sample could have gone maybe. And then if you go to that resample table and you get it looks like this original one, you go to the age column and you get the average. That will be the average age of that sample, that resamples, that bootstrap sample. All right. So go to the age column and then get the mean. Dot mean would work. And so that's that can turn into a function like def1 bootstrap average. Make another sample. Do a bootstrap sample. Right there. There's our resample. So sample from the original. Sample again with replacement this time. So remember that this is by default dot sample with nothing means same size and with replacement equals true. All right, so I'm getting the same, another 100 rows from my 100 row sample, but some of them have maybe been duplicated. So it's a bootstrap sample. It looks like my original sample, but it's a little bit different. It's trying to pretend to take care of any, what's the right word? It's trying to look like the original population, maybe in a slightly different way. That's kind of how it's working. Okay, so that is my function. I can call that 1,000,000 times now. So this is our goal. So we want to generate a resample from our original sample and give back the average age. That's what we're doing. All right, resample or bootstrap sample from our original sample and give back the average value for what we care about. So that should be a return there. And so now I can call this a bunch of times, and like my sample's average age is that, apparently. But if I do a bootstrap average, take a bootstrap sample and take the average, it looks like it took a couple more younger people more often in that sample. And so this could very well be a better, more indicative of the actual population. There could be more younger people after all. We don't know. Our sample could have looked a little bit different. This is giving us a similar sample that does look different still. All right, just kind of weird to say and explain, but I hope you see it. So the idea is this is helping us see what our population really could have looked like. And so if we do a bunch of these, we have a better picture of the population. Okay, a better picture of the actual Titanic passengers. Even though we know the real answer, we're gonna compare against what we find. Okay, so let's do maybe 500 or no 5,000. Let's generate averages from 5,000 bootstrap samples. Might take a while, but I want to do repetitions equals 5,000, let's say, and then I want a bunch of bootstrap averages or bootstrap means. So make an array, starts out empty, and then 5,000 times for I in np.arange repetition. So again, I'm just using this I variable to keep track of, have you done 5,000 things yet? It's just going to run the body of this loop 5,000 times. I is going to range from 0 to 4,999, and I don't care about that at all. All I care about is that it's running the body 5,000 times exactly. And then every time I'm in this body, I want to say one bootstrap average. Try to get another bootstrap sample, get the average age for that sample, and that's going to, if I do this a bunch of times, it'll give me a better picture for how the actual average age looks in the full passenger list of the Titanic people. All right. So np.append to the original bootstrap means that one, and then set it back equal to, because np.append does not modify anything. So there we go. So I've got now, if I run this, it might take a second because it's got to shuffle things around. But does it make sense what I'm doing here? So I'm doing this 5,000 times, I'm getting a bunch of different resamples, and I'm getting the average age of that resample, which is going to be a bit different than the original sample's average. This maybe is a good number that is indicative of the population, but this one is too, is the idea. This one also is. If you do a bootstrap average, that's also a good estimate. If you do it a bunch of times, that helps you see how your sample could have varied if you took a different one. So yeah. Once we do that, we can do a histogram. If you want to see stuff, you can be like table with a column called, I don't know, averages. It doesn't really matter. Averages is bootstrap means. I guess it's average. Bootstrap means. And then you just immediately do a histogram. And it looks like we see that it could have been the average age of the Titanic passengers, given these bootstrap samples, could have been over here, could have been a little bit less than. It still is not too uncommon for us to get a random sample that is like 27 years old. It's not too uncommon for us to get a random sample that's, bless you, a little bit older as well. So kind of, it's going to range around the original sample's mean. But this is going to give us how our sample could have gone in a different universe if we took a different one. All right. And so I've got a bunch of bootstrap means. If I look at that, it's just a big, long 5,000 sized array. very, very long. It's got a bunch of things in it. It's a bunch of different average ages for my bootstrap samples. And so if I do percentile stuff now, then I will get a confidence interval, right? So if I go to the 2.5th percentile and the 97.5th percentile, in between lies 95%, right? So that will give me what I want. So get a 95% confidence interval for the average age, and that's if I say percentile, I want the 2.5th percentile for my bootstrap means, bless you, and then I would also like the 97.5th percentile for my bootstrap means. Oops. And if I see both of those at once, this will be like the value that's less than or equal to 2.5 of the values. This will give me the value that is less than or equal to, or sorry, that's greater than or equal to, I think. Yeah, that's greater than or equal to 97.5 of 97.5% of the values in my bootstrap means array. And so here is my range, and this is my 95% confidence interval. We are confident that this will hold the right thing 95% of the time. That's how we say it. So yeah, this value, this range will hold the true average age 95% of the time if we do it right, if we redo this again. And we can compare this is our estimate, right, given our bootstrap sampling method on our original size 100 sample, but we actually have the full list of Titanic passengers. We can see how good this bootstrap process was and prove that it is a good idea. All right, so we can compare it against the actual average, right, actual average age for every passenger. And that's Titanic. Just go to the original Titanic table, go to the age column, and then get the mean. And that was 29.7-ish years old. And that is within our 95% confidence interval, so it worked out. How does this compare to the samples average? Not horribly off. 29, a little younger, but still 29. So yeah, that is that's the story. You can get a good idea of how your population looks and how it might vary, how your numbers might vary if you took another sample by just making another one up on the fly by sampling from your sample. That's bootstrapping. All right. Any questions about that? It's a fun little process that is surprisingly powerful. All right. Next, we should talk about regression, right? The idea of we want to, first of all, find a number that represents how linearly, like how well our, like an x axis and a y-axis correspond, like x values and y values correspond together. If you just scatter plot, like how well do they lie on like a straight line? So that's what linear regression is all about. That's the correlation value. We can calculate a single number that represents how linearly correlated some two variables are to each other. And then that correlation value, with some fancy math, gives us an actual line that is the best one that you could draw through your data that helps you, and you can use that for prediction. It helps you see, like, okay, if I got a new value that wasn't in my data set, what's the best value I should predict for it, assuming that it was a linear relationship truly, okay? So yeah, let's do the son's heights.csv file with the father's heights and the son's heights, and also the mother's heights, but we saw that the father's height was better correlated. So, boop. Father and son. Let's compare the two. So son's heights data set. We got that one. Let's get out the father and the son only, and that will be our table. So I got a bunch of father heights and son heights, and let's see, how do I want to do this? Let me type in the first two, and then I'll paste the other ones. So the way that you can calculate correlation is it's a number, it's a product of values. It's like the x values and the y values when it's the average of the products when they are in standard units. If you go back to the formula, and so let's write all that out. So there's a function that we need that first of all can like take a like give me an array, give me a column. Let's convert those numbers to standard units. How far away are they from the mean in terms of jumps of a single standard deviation? So standard units. You give me an array of any kind. It's going to end up being a column. I'll give you back the standard unit values for all that data. So if I give it a doc string, it converts an array to standard units, otherwise known as z-scores. Remember that word as well. So z-score is just how it's the same idea. So it's a number that's in standard units. It's how far away am I in terms of multiples of a standard deviation am I away from the mean. Okay. So I can very quickly do this with array notation with NumPy stuff by saying, all right, take my array. How far are all the elements away from the average of that array? So np.mean, that array. How far away are they all from the average? So subtract the average and then divide by the standard deviation as well, divided by np.std on that array. So that will give you in units of how many standard deviations are all these values away from their means. I return that, that's that array in standard unit form. Does that make enough sense? Remember those words? They're all converted to z-scores is another way to say that, all right? And then correlation, the correlation coefficient tells you how, you give me a table, you give me the name of an x column and a y column, though you can flip the two around, correlation is symmetric. This will give you the correlation coefficient R, right, that tells you how linearly correlated that x column's value is to those y column values. So that's how that works. This function will compute the correlation coefficient. Correlation coefficient R. T is a table, and x and y are column names. All right. And so the way that you get correlation coefficient is first you convert those columns, those arrays of those, like the x values and the y values that want to find how correlated they are. You convert them to standard units. So it's like the x values in standard units is, you call your standard units function on that column, t.column with the x label. And then you do the same for the y. So the y column in standard units is exactly that. And then the answer, the way that you do the correlation coefficient is you multiply them, x standard. It's just, I have no easy way of proving to you that this is why it works. This is the right way, but this is the formula, right? You multiply the values, the corresponding values, x values and y values in standard units, and then you take the average, and that will tell you how correlated they are. If it's a positive number close to 1, that means they're like they go hand in hand. Like if one increases, the other also increases in a linear fashion. If it's close to -1, that's still highly correlated. That just means that when one increases, the other decreases. They're inversely correlated. So that's the value. That's the correlation coefficient. Okay, so yeah, and then everything else, that correlation coefficient generates the best also line that goes through the data, because we're assuming linear stuff. And all those formulas I don't really want to write down too much. So I don't want to type those all out, so slope. So all these functions, I'll just copy and paste. But the first two, those are important to remember and understand. Oops. Copy. There we go. So like the slope of the regression line involves the correlation coefficient. It involves standard deviations of the x values, x columns and the y columns. You can solve for that. You can solve for the slope, get it back to normal units. You can solve for the y-intercept of the regression line in a similar way. There's a formula. And then fitted values is a function that takes, that's just like you give me the x values and the x column and the y column for a table, and I will calculate the best line through it, and I will give you my prediction, right? The prediction for all the x values that may be a little bit off from the y values, but they're my best lines prediction for those values. Okay, so that's what fitted values means. And so once we have all those, we can say, all right, sun's heights. We can do a scatter plot for father and son, and like the whole point of you'd probably do that first and notice like, oh, okay, when one increases, the other increases. That seems to be decently correlated. What is the correlation coefficient? I can just do this in one cell, actually. Correlation of sun's heights, where we are trying to see how well father can predict sun. So father on the x, son on the y. That's about 0.5, which is decently positively correlated. All right. And so if you wanted to use your slope and intercept, you can make the line. You can calculate what that line should be. But the scatter plot itself can do that for us. Fit line equals true. It will display it for us. And so that's like the best line that will run through our data, and we can use that now to predict new values. Right? We can use that now to predict new values. So like you say, you give me a new person, and that's not part of our data set, and you say that, all right, the father's height is 70 inches, and they just had a son, and we're going to predict them that the son's height is going to be a 71-ish inches. Okay? That's what we're going to do. And that is the best prediction given all of our data. That's what it means to be linearly correlated. All right? And that's what regression is all about. So let's see here. Does that make sense so far? Coming back to us? Yeah. So, yeah, for every x value, so like we've got our table, right? Sun's heights. Let's store our prediction, because this line makes predictions, right? Let's store how good of a prediction for each father height. Like, what's our predicted sun height? And we can compare that and calculate an error, right? We can do all those things. So, well, let's do that. So let's get the slope. Dun, dun, dun. Let's get the slope value. That's m, I guess. And I want to get the predicted values for each father. I could be using, technically, right? I could be using that fitted values function, but this is better. Could use fitted values, but this is more educational. All right. So fitted values is what you could be reaching for right now, but we're going to do it slowly. So give me the slope of the best line through this data. And that's sun's heights, father predicting sun, and then the intercept is a call to the intercept function. B is intercept. We got that guy. And then our predictions are, you give me all the father heights. I can multiply that height by m and add b to it, right? Like plug it into that function, y equals mx plus b. That's the father value is the x. Okay? And that will give us our predictions. So you give me sun's heights, column father. Those are my x values. I'll use those to predict the sun's heights using my best fit line by multiplying all those values. Like that's the x. So m times the x's plus b. That gives me all my predictions for each value in the father column. And we can attach it now, and we could bring it as part of the table and be like sun's heights dot with column predicted sun height. And then our predictions can go there. And we can call this, I don't know, heights with predictions or something. Something like that. And so for each father height, this is the predicted sun height for that father height. And it's never perfect because it wasn't perfectly 1.0 correlated, but this is the best value that we can find. All right, these are the best predictions that we could find. And so we can also generate this graph kind of manually now by scattering both of these. So sun's heights dot scatter with father on the x. Oh, sorry, it's not sun's heights, it's heights with predictions now. Dot scatter with father on the x. You can see our line there as well for each actual value for the sun's heights. All right, so there's that one. Are there any questions about that idea of the prediction, the predicted value? It's not perfect. It's just our best fit lines prediction. For each x value, we're using the father height to predict the sun height. We're assuming there's a linear relationship going on. And there's a decently linear one. But we can also ask the question, how far off are all of these things? Right? That is, so we drew the regression line, we just drew it manually. We can ask, what is the error, right? What's the root mean squared error, the RMSE? where the value of an error is like how far off were we from the prediction. So like how far off was our prediction from the actual value. The value of an error is actual minus prediction. And so let's find that. Let's find the error. Okay. How far off are we for all of these? It's just kind of going to be like, all right, the actual sun height was 73.2, subtract our predicted sun height. We're predicting too tall of a sun for that one, unfortunately. And so we'll have like a negative error. Like we should have been brought down a little bit. So let's calculate those error values. So errors equals heights with predictions dot column sun minus heights with predictions dot column predicted sun height. There. Those are the errors, and I can attach that. Not with a column. Errors. Those are my errors. Oops, what have I done wrong? Table object is not callable. Oh, sorry, yeah, dot column. Predicted sun height. That's a very long line, sorry. So yeah, there's my additional column there. It's like, all right, this one was off by negative 1.98. This predicted sun height was a little too tall. So the actual height minus our prediction from the regression was a little too big, and so we get a negative error. Same with this one. It was a better guess, though. That's good. Only off by a little bit. And then sometimes it's also a positive error, right? We like the father's height. The father was short, but the son was much taller. So it's never a perfect comparison. Maybe we need like grandfather heights and things to do it even better. I don't know. But our predicted sun height was that. So actual minus prediction was a positive value. We're off by a positive amount. We should have added that. That would have done it better. So yeah, that's how that works. And there's a single number that we can use to represent how far off were we always. It's like an average kind of error. It's called the root mean squared error. Okay. Root mean squared error, because sometimes the error is positive, sometimes the error is negative. So if you add them up, it might cancel each other out. The very first thing we're going to do is square these errors to get rid of all the negatives. That's the first step to make sure we're going to count all the errors properly. You could have also done absolute value. That's another kind of error calculate. It's not root mean squared. It's root mean absolute value error might be. I don't know. That's a possibility. So the very first thing you do to calculate the root mean squared error is you square the error. So you do it backwards. Give me the squared errors first. So errors squared gets rid of any negativity. So errors, now they're all positive values. Some are very large, some are not. And then the next thing is you get the mean of that, the mean squared error. That's actually a thing in itself. The mean squared error is take that and give me the average mean. So the mean squared error is that value, but the units are off now. It's not in inches anymore. It's like in inches squared because we've squared the thing. So to get back to the original units, we take the square root. We root the mean squared error. All right, that's how you do it. That's the root mean squared error. RMSE is equal to whatever that was to the 0.5 to take the square root, and that's the root mean squared error. And so this is like on average, we're about 2 inches off in our prediction, which isn't horrible. Okay, so that is that's how you do it. That's one value that kind of tells you how far off are all your predictions at once. Yeah, so I think that's what I wanted to say. Are there any questions about that calculation, that idea? It's a useful number. Tells you once and for all how bad you did. And then I also should tell you that the regression line, this correlation coefficient is predicting a regression line. That is the best line that minimizes root mean squared error. That's the reason we learned it. So I can prove that to you. Our regression estimates for the slope of the regression line and the height of the regression line, those are our M's and our B's that we solve for here. That's what regression says is the best line through everything. And those are minimizing the root mean squared error. So like that was the slope, that was the y-intercept. And what that means is those are the best ones you could possibly do to minimize the root mean squared error of your predictions. So I can prove that to you by using the minimize function. Remember that one? So the minimize function, where is that? over here somewhere. There it is. The minimize function takes a function that gives you the inputs that would give you the smallest answer. So what I'll do is, let's make a function that calculates the root mean squared error for, like, you give me your best guess of slope and intercept for the best prediction, for the best line through your sun's heights data, and I'll give you the root mean squared error for those predictions. So I'll make a function called root mean squared sun height. You give me your best guess for M, your best guess for B, the slope and the intercept of that regression line, and I'll give you the root mean squared error of you using those for your predictions. So the x values are sun's heights dot column father. The y values are the actual values we're going to compare against, because we're making predictions, right? These are the actual values. Y is the real thing, the real values that we're trying to predict from the x's. And our predictions are, right, take all the x values times your best guess of an M plus B. So our predictions are mx plus b. Those are predicted sun heights. And so now you got y, the real values, and predictions, the predicted values, for your best guess of this line that goes through everything. The errors are, you take the y's, subtract the predictions. Oops. And then the root mean squared error of that is, like, you take the errors, you square them, you take the mean, and then you take the square root, and you return that. So you give me a slope and an intercept, I will give you the root mean squared error of using that to do predictions. Okay? So you can give horrible values like RMSE, sun height. Let's say we want the slope to be 1 and the intercept to be 15 or something. I don't know. That mean, if we were to use that guess of the slope and that guess of the intercept to do the predictions, we are off by an average of 14-ish inches. So that was a bad prediction, yeah? So if you gave me some values for M and B, we would like the ones that produce the minimal root mean squared error, and it will end up being the ones that we had all along. That's what regression gave us. Those are the best ones. So if I say minimize now, that function, RMSE height, RMSE sun height, I do also have to say smooth equals true. Don't try to pretend this is a smooth function that we're trying to minimize. We find the exact same slope and intercept that we solved with from before. And so that goes to show that this regression line is a good line according to our definition. It minimizes the root mean squared height, or the root mean squared, yeah, for this example, the units are height, inches. It minimizes the root mean squared error of our predicted values. And so that is why we should use that one if we think it's linearly correlated. And I think that's what I wanted to say. Any questions about that? So that's a good one. And then you could also do bootstraps here. You'd be like, because these are just a few fathers and sons, right? These are just a few fathers, not the whole world population census of all the fathers and sons in existence. We can do a bootstrap prediction for, like, what is the true slope of the regression line for all men on Earth? Something like that. Assuming that our sun's heights.csv was like a good random sample of everybody on Earth. Maybe it was like US people or something. I don't know. So we can do that. We can do a bootstrap sampling to find, like, what's a good range that the slope should be in, because I know that this isn't every father and son, like in the US or something. Let's see what it could have been. Like, what's a good range that we are pretty confident that the true slope lies in, if this really is linearly correlated and this sample is a good sample. Okay? So yeah, we can do that. So repetitions equals, like, let's do 2500 or something, because this one will take a second. So let's create 2500 bootstrap samples. Find the slopes for those samples. We resample, we get new slope values, right, for the heights of the suns, right? The father's predicting the sun's heights. Find the slopes and save them all. So we can see, like, all right, how often do I predict these smaller values than the one that I see from my original sample? How often do I predict larger values? We can do some percentile calculations and get a confidence interval. For I in NP to A range, repetitions. What do I want to do? Well, let's make an array of slopes first of all. Slopes equals a blank array. And then I'll go through it, and I'll take a sample to get a bootstrap sample of my father and son data. So son's heights dot sample. So if I just say sample like that, by default, it's getting me a bootstrap sample. It's going to take as many rows as there were in the son's heights table, and it's going to do it with replacement. So sometimes you'll get more of the same people, less of other people. Sometimes you won't even get, like a row will be not included to have some duplicates of a different row. So we're going to pretend that that's a better, like that's telling us what the population could have been like in a different way. If we took a different sample, what would we have seen? And we can get the slope of that. So bootstrap slope now is give me the slope of that bootstrap sample table. Again, where we're using the father's height to predict the son's height. So that's the slope of our bootstrap sample now for its regression line, and we can keep track of what that one was. Slopes dot equals slopes. NP dot append slopes to like that new bootstrap slope. So there we go. And yeah, after we've done that, let's have that run. After we've got it, we can do a 95% confidence interval. So find the endpoints of the 95% confidence interval for the true slope. Right? The left is the 2.5th percentile of those slopes, and then the right is the 97.5th percentile of those slopes, where you've got 95% in between. And so what are left and right? It looks like they're pretty different. So it looks like 95, if we were to rerun this 100 times, 95% of the time, this range holds the true slope of like the heights for like to use to predict the heights of sons from their fathers in the US, let's say. So yeah, the slope could be, it seems like it could vary quite a bit, because maybe we needed a bigger sample. That would have given us a better, a more tighter confidence interval. That's one way to fix that. But yeah, also just people's heights, they vary. It wasn't perfectly correlated, and so this is kind of accounting for that. It was just 0.5. It wasn't 1.0 or anything. So yeah, that was a good one. That was a bootstrap to discover like what should the true slope. What's a 95% confidence interval for the true slope of that regression line for like all the fathers and sons ever, or at least the ones that this sample represents. So yeah, I think that's what I wanted to say there. Are there any questions about that example? So a lot to do with regression, good examples of bootstrapping as well. Root mean squared error, all that fun stuff. So yeah, that was that. We've only gone 2 slides. It's funny. So there's really only like 2 more chapters though to talk about. Are you ready to go over classification again? That was much more recent, and so we don't have to spend too long, I don't think, but we will anyway. So the idea of classification is we're trying to predict a categorical thing, right? Like in this case, for this example that we did before, it was like, was there breast cancer, or was it like malignant breast cancer, or was it benign breast cancer, something like that. So that's like a 1 or a 0 where it's not numerical. When it's not numerical, it's like a yes or no value. You can do the same thing for other things, like we predicted different kinds of wines, right? We predicted did a patient have chronic kidney disease? All those things, did they not? So that's what classification is all about. You're predicting categorical things. Categorical stuff, let's say. And our classification algorithm that we learned about in this class was k nearest neighbors. So you go and you find, like, all right, here's your data set. Go arrange the numerical pieces of your data set in a very large dimensional space, and you say, all right, you come along and you say, all right, I've got a new person. Here's where they lie in that large dimensional space. You pick a k value like 5. You go and find the closest in terms of distance to these points in space, which we have a distance algorithm for, distance formula for math. Like, go find the 5 closest things to this. That one, that one, that one, that one, and that one. And like, depending on what class they were, like some of those were one class, some of them were another. Like some of those were blue, some of those were rainbow, let's say. Like this one was a rainbow one. This one was also a rainbow one. You take a majority vote over the class that you see. And so it looks like to this green dot, the closest, the 5 closest things, if we're going to do five nearest neighbors, were of the blue class. Those ones win. And so we're going to predict blue. Boop, boop, boop. That one wins out. So we're going to predict blue. Predict. That's probably a blue dot. It probably was the blue class rather than the rainbow class. Does that make sense? Coming back to us. So that's what classification is all about. To make sure your classifier that you're training, right? That's the technical term, right? To make sure the classifier that you're training is doing a good job and it's not memorizing the data, you should be splitting up your entire data set into a training set and a test set. So you're going to save away some of your data. Like, here's all your data. You're going to split it up and be like, all right, some of these things, you're going to shuffle it, of course, but you're going to save some of these things to be training, some of them to be testing things. So you're going to train your model. You're going to find the closest things in the training set. Training, and test. So you're purposefully giving up some of the things that you could be comparing against to just make sure you did it right. All right. So there's your training set, your test set, and then you use to come up and find the accuracy. You're going to take everything in your test set and you're going to run it through the model that you've come up with using your training set and see how well it did to do the right prediction, because you know the actual class of all these test elements. So that's kind of that in a nutshell. I think an example is worth 1,000 words. So let's redo our breast cancer example. Yeah, any questions about that before I go there, though? This is pretty recent, so hopefully it's still kind of fresh in our brains. Classification. And so, let's see, so our patients, we'll call the table patients, table read table, that's breastcancer.csv, and there are a bunch of, like, in this table, there are a bunch of different people that were of different classes. If I do a sample, you'll see some class 1s and class 0s. Class 1s and class 0s. I assume that everybody in this data set had breast cancer, but like I think 0 is maybe like benign, 1 was malignant, something like that. We want to determine the difference through classification. One of the columns, because you don't put people's names in this, right? You don't want to like have us trace back to them. They use a patient ID, and this is a number that has nothing to do with breast cancer. Right? That's just a random number kind of that they came up with for these patients. And so we should not be comparing against these at all. That's one very important thing. It is a numerical thing, but it's not something we should care about. So let's drop the ID for these patients. And so now everything else is normal numbers that have to do with diagnosis, as well as this class label at the very end. Okay? And so how many patients do we have? We got 683. One easy way to do a training and a test set split is just like to use half. When you don't have enough, sometimes you usually give more to training than to tests. Like you do a 3/4 training, 1/4 test. That's the thing, potentially. But half is fine. So 683 over 2. That doesn't go in perfectly cleanly, and so let's give the training set one more thing than the test set. So the way that we're going to get a training set and a test set was we're going to shuffle everybody, because the order was like, there were a lot of 0 classes at the start. I did a sample here, but if you remember, there were a bunch of 0 classes at the start. So we want a representative sample of like for our training set and for our test set. So let's shuffle everybody. With replacement equals false, don't duplicate anything. Keep the same patients. Don't like clone a patient or anything. Don't delete a patient either. Get them in a different order so I can make a training set and a test set that was random. Okay. So patients.sample, give me the same amount. I could say 683, that's fine. Or I could say patients.numRows or something with replacement equals false. And honestly, 683 is a default. Just like with replacement equals false, I could have said. But I'm spelling it out. Take them all with replacement equals false. And I can split this up now, this shuffled patients table, into a training set equals something and a test set equals something. Okay. So the training set, let's take the first 342, I guess. So shuffled patients.take the first 342. Boop. And so that'll be indices 0 through 341, right? That's what MTBL-A-range is going to compute. And then the test set is everybody after that. So that is from 342 onwards, right? Because this one doesn't take up to 342. It goes up to 341. So start at 342 and then take onwards to index 682, right? Because it goes from 0 to 682. It always starts at 0, so it's 1 off. But if I say 683 here, excuse me, I should be saying, if I said 683 here, that's what I want. So that will give me everybody else. All right, so there's my training set, there's my test set, and now I can train my classifier. I can see how well it does on the test set, and we've got a bunch of functions for that I'm just going to copy and paste because that would be a lot of typing. Okay, but that's our setup. Does it all make sense how we're like why we use with replacement equals false here? And understand the purpose of splitting up into training and test, stuff like that. All right, so let's bring in the cavalry. We got this one. Sorry. So distance. So I want all these cells right here. Boop. There's a lot of functions. Let's go through them all though slowly. We got the time for it. So the very first thing is like going back to this drawing. When we do have it, we've got it split, right? We're going to use the training set. Like you give me some new point in the test set, really. But you give me some new point, I'll go put it in this high dimensional space, and I'm going to go find the closest 5 or so, whatever k things in the training set to this new point. And so I need to do a distance calculation. I need to do a distance calculation over every single person, every single individual in this set. For every dot, I need to know how far away the green dot is from it. Does that make sense? I need to know everybody. Otherwise, I might skip somebody accidentally. So we need distance. So the distance calculation is in every dimension. It doesn't matter. It's like you give me an n-dimensional point and another n-dimensional point. It's just like you take the differences of each of those coordinates, like the x's and the y's and the z's and like all the other things as well, if there's more. And there will be more in this example. How many dimensions do we have here? 1, 2, 3, 4, 5, 6, 7, 8. There's 9. All right. There are 9. So this is a 9-dimensional space we're putting all this breast cancer data in. That's fine. We're subtracting all those 9 coordinates, the x's from each other, the y's, the z's, the p's, the q's, whatever you want to make up the letters for. And then we're squaring them, and then we're taking the square root. So it's the Pythagorean theorem kind of distance formula. The square root of x1 plus, like here, the distance from x to, from 2 points, x1, y1 to x2, y2. That's just the Pythagorean theorem. It's the square root of the x1's differences squared plus the y differences squared. And if there's more coordinates, you just kind of keep going. That's kind of the formula, right? So this is that in NumPy form. All right, you do the subtraction first, do the subtraction of all those coordinates, the corresponding ones. You square each of those, so there's a squaring. Then you add them up with the plus, np.sum, and then you take the square root of all that. All right, so that's the distance formula over everybody. So there it is. And then what we want then, once we have that ability to define distances to points is you give me some new point that I haven't seen before, call it a new row maybe. This is like a new place in the table. We're usually going to be getting it from a table. We want every single distance from the training data to that new point. That's what I need. So all distances gives that to me, all right? So we're not going to use the class as part of the numbers because like we don't have the class for the thing that we're trying to predict. That's the whole point. So we're going to drop the class label, and like everything else is fair game. That's my 9-dimensional space. So those are my attributes. This is everything in the training set except for the class. Those are the numbers that represent that idea of that point. And then I want to find the distance from this new row to each of those points in the training data, forgetting about the class. All right, so I chop that off for a split second, and then I try to do my calculation. So for all of these, right, forget about the class. Got a new point. How far is it from this row? How far is it from this row, that row? All those guys. Okay. So that's all distances so far. And then the easiest way to do that and to get those distances as an array is make a function and apply it. Right? Make a function and apply it to the existing table. Okay. So we're going to make a function that takes you're going to apply it to the entire row of the table at once. And so like for each row that you give this function to, like you give me a row of the table, I'll give you its distance from that row and all its values, you turn it into an array, to the, from the new row to that row. And you could have done it in the other order as well. So either way, it's like, all right, for some row you want to give me in my training data set, take the new row, see how far away it was from that one row. You got to give distance to the distance function arrays, and so that's why you do that conversion there. Like that's a function now. I can apply that function to this table, and those are my distances for each of those individuals in the training set to the new row. Do you kind of see how it's calculating that? It's finding the distance from every value, every row in the training set, because we're doing an application of this function, to this new row that's like the green dot. This is a new thing that I don't know about yet. How far away is everything I know about to that? That's all distances. It gives you back every single distance in order. And you can attach that to your table if you want to. Okay? We get so far? So we talked about this once, but it's very complicated, right? And then we want to find the top k, right? We have all these distances. Now we have that function that computes these distances. Go and find the top k rows with the closest distance to this new point. So again, we've got a training set. We've got this new point we want to find all the distances to, and we want the top k, right? We want the closest k things, all right? So first we need to find all the distances with our all distances function, and then we attach that distance to the training set. There we are, training set with all the distances. And then we're going to sort by those distances. That's how it works, right? Compute a new table, sort by the distances in ascending order, and then just take the first k. Does that make sense? Take the first k. They got the smallest distances that we've attached and calculated in the way that we know how. And that is my table of k nearest neighbors. Those are the k nearest things to me, k nearest rows in the training set. Yeah? I've got them now. That's like these ones. The rainbow dots and the blue dots, the 5 of those if k was 5. Okay? Got those. And then I need to find, because usually you're going to use an odd k, right? You're going to use an odd k, and so majority is going to work out always. So what is the class? What is the class that I should predict? It's the one that has the most representation in that set of 5 things, or whatever k things there were. And so I'm going to go through that nearest neighbors table and find the majority then. Right, that's my goal. You give me a nearest neighbor table. I know that the class column is the thing I care about. Go and find the class that has the highest representation. So the majority of you give me a nearest neighbors table, I'll give you the majority class of those k things. So if you know there's just ones and zeros like we have in this example, you're just like, all right, how many ones are there? How many zeros are there? Where you do like a dot where and you count the rows that you get back. How many ones are there? How many zeros are there? If there are more ones than zeros, then the majority is 1, right? Otherwise, it was guaranteed to be 0 because your k was odd. Yeah, guaranteed to be less than, not equal to it ever. So that's how you find majority. And that gives us k nearest neighbors, doesn't it? It's like those two functions together. Call nearest, then call majority. Yeah? It's like, all right, you give me a training set. You give me some new point that you want to find the closest k things to. There's k as well. I'll give you the right class that I think it should be. I'll do k nearest neighbors on it. So you calculate the nearest neighbors table for that new point. Give me the k top things in terms of shortest distance, smallest distance. Give me all those things, and then give me the majority class for it. That's k nearest neighbors in a nutshell. That's a very short implementation, but like the heavy lifting was done by all those other functions that we wrote. Yeah, that's k nearest neighbors, and that's how we make a prediction for a new point. Isn't that lovely? Does that make enough sense? You see how it's all working together there? So that's what I care about you understanding. You got that going on, and then you can finally play this game again. It's like, all right, I made a training set, I made a test set. Go and use the test set. Forget about the class for a second. Pretend we didn't know. Use the training set to predict the class of everything on our test set. Go and see if the predictions match. That tells us how good of a classifier we just made. All right, that will be evaluate accuracy. Give me a training set, you give me a test set, you give me a k value. I'll do k nearest neighbors using every row of the test set. I'm going to make a prediction using the training set. All right. So the test attributes is everything but the class label, because we're not going to use that for prediction, right? We're just going to pretend we didn't know it, see what our classifier would have said. And so like you give me a row of the training set, or sorry, you give me a row of the test set, a new row. I'll do k nearest neighbors on that row, and I'll tell you the class that I think it should be. That's what this function is computing. Give me a row of the test set. You do k nearest neighbors. I will tell you what I think the class should be, because I'm calling k nearest neighbors on that row with the training set. And then if I apply that function to all of my test attributes, I get the predicted things, what my training set on using k nearest neighbors predicts for all of my test set. Does that kind of make sense? Apply that function to all the test attributes, forgetting about the class. Here are the predicted classes for each row of the test table using the training set and k nearest neighbors to do the predictions. There they are. And then you just want to go and see, like, I know, I have the actual column called class in the test set. Go look at that. Compare it to the predicted classes for each of those rows. See how well it did. See how well it did, and do like a percentage calculation there. And that tells you how accurate, to some extent, your classifier was. You can imagine that the accuracy changes depending on like your random shuffling of the training set and the test set. Maybe you got better, more representative data the first time you shuffled it rather than the second time. So that's possible. But in theory, if your data is good and random, it shouldn't matter how you split it. But that's every one of those functions. Do they make enough sense together? Definitely go study them. They're very important. But now we can say, we can do our test, right? How well can we predict class 1 or 0 for this breast cancer data set? So we got a training set and a test set. Let's see how well we can calculate the class of like malignant or benign breast cancer, perhaps. Evaluate accuracy using the training set and the test set that we've computed those variables. Let's do 5 nearest neighbors. It's going to take a second. It's got to play this game. Got to make a million different tables, right? And it looks like we are about 97% accurate for using that data to calculate and predict class 1 or class 0. And that's lovely. That's very, very accurate, and that's very useful for doctors and things. So that is definitely a cool place where data science is in use, or machine learning is in use, because this is technically a machine learning algorithm. We're learning something from just data that we were given. It's awesome. All right. Any questions about that whole process? Kind of see how it goes together. Remember it. This is very recent. The last thing I want to say is remember, don't forget that sometimes your rows, like the range of values that you might have in these rows, like clump thickness, uniformity, and stuff. So you see, like these are like 1s and 10s. These are like usually less than 6, I guess. These values are like kind of all over the place. If you have weird ranges for values, like this one goes from 1 to 10, this one only goes from 1 to 5, it's going to prefer, like when you're doing distance calculations, right, it's going to prefer the bigger differences, isn't it? And so you want to get every one of your columns, if they're not already on an even playing field, do it by making every column in standard units, yeah? Because then you're guaranteed, right, everybody to be between like 1 and -4 to +4 standard deviations, even if it's not normally distributed. You're golden there. So that is why that is sometimes useful. If you have wild, remember, if your columns use, what's the best way to write this down? If your columns values have like different magnitudes, if their ranges are wildly different, if the range of values for your columns are widely different from one another. For example, one column ranges from like 1 to 10, like the values range from 1 to 10, and another ranges from like 1,000 to 9,999, something like that, then you really should probably be using standard units. Then it's a good idea to get every column on an even playing field by converting them to standard units. Again, aka z-scores. That way, everybody's going to be between like -4 and +4 for sure. You're pretty much set. They're all relative to one another. If you don't do that, your distance calculations will, I don't know, they'll be skewed. What's the best way? They'll be biased. We'll be biased in favor of the differences of the larger things. So I think that's how I want to say it. Does that make enough sense? Don't forget about that. I think we were fine enough. We got decent accuracy as well. We were okay enough for the values that we were given in this data set, but that's not always true. All right, remember that I showed you one from the chapter 17 stuff where that really was not true. We got a much better accuracy when we did standard units first. So yeah, I think that's what I wanted to say about that one. Any questions about classification? Yeah. Sure, yeah, we've got a nice function from our regression example to do that. That would be, oh gosh, I went too far. This one. So we got a standard units function that takes an array. So what we would do is we go and use every single column. So like we've got, gosh, what's the original table? It's called patients. So for every column of patient, we'd be like patients dot column 0, get that out, and then we can apply standard units to that column. And then you just put it right back in with the same name. Does that make sense? Yeah, just do that for every single column. And then you got them on a nice even playing field with one another. Great question. Other questions? All right, I think we're good to just go over the last chapters. There's some other stuff from like Berkeley that I could have used, but I think we perfectly hit the end of the book right on time, it sounds. So the last thing let's talk about is Bayes' rule, where you've got some probabilities, you know them, but you really want a different one that you don't know. You'd really like to flip things around. So remember that you can gain new knowledge when you're doing prediction calculations, when you're doing probability stuff. So like, let's remember what this table was, right? It's like there was a class full of people, class full of students, and some of them were second years, some of them were third years. You knew that like 60% of them were second years, 40% of them were third years, something like that. And you knew that for every second year student, it was kind of a 50-50 split of did they declare their major, did they not? Because they're young, right? They're still free. They're trying to figure out what to do in life. But the third years have locked it down, right? If you have a third year student in your class, you know that 80% of them have declared their major by now. They're ready to go. And only 20% are still undeclared, okay? So you know all those things. You'd really like to know, like, I take a student by random. I draw a student randomly from the class that has this makeup with these probabilities. I'd really like to know what's the probability that I get a second year student. I pick a random second year student, given that that student tells me, like I pick somebody randomly, I call them their name, and I ask them first, did you declare a major? And they say yes. Like that has now changed the makeup of the world. So like this calculation, you say this, the way you read it is like the probability that I find a second year student given that I know that they've declared their major. See how you read that? Remember that? So what's the probability of getting a second year student given that you know that that student has declared their major? So like you ask randomly, you call on somebody, you ask them first, have you declared their major? They say yes. What's the probability now that they're a second year student? Does that question make sense? It's not going to be the same. It's not going to be the same as like 60%. Because you know that the second they say they've declared their major, they're either here or here, right? And that has changed the makeup of like how many people could be in those places, right? You know that they're either there or there, and there's a different spread at that point. So like you're conditioning. It's called conditional probability. So you're conditioning by something that you know now. Like this is new knowledge. Given this is new knowledge. All right. Sometimes this kind of just comes for free. Like in this diagram, 0.5 is equal to the probability that you see it, that someone has declared their major given that you know their second years. You see how that's 0.5 and you just read it off the table? It's like, all right, you knew that they were a second year. Here we are. The probability that you have a declared second year is 0.5. So like, given that you know this, the probability that you see a declared major is 0.5. Like that's part of the table. The flip of that is not part of the table. The flip of that is not part of the table. And so, yeah, let us talk about it. So the way that you calculate this, right, is with Bayes' rule. Here it is. Here's how you can flip it. This is what it means. This is what you're allowed to do now. If you would like to I want the probability of A given B, it happens to be equal to the probability of B given A times the probability of A over the probability of B. All right, and so let's do that exact thing that we did last time, last chapter, right, the very last chapter of the book, and that'll be it. Let's see here. I want to make sure I don't mess it up, so let me do it. So probability of second year given that we know they've declared their major is equal to is the probability of declared their major given that they're second year. All right, so that one we know, that's 0.5, times the probability that they're the second year, all right, over the probability that somebody has declared a major, all right, probability that you can just get a random student and know that they've declared their major. Probability that someone at all has declared their major. That one's the hard one to find. The rest of these are kind of easy. So the way that you can calculate probabilities in this way, like what's the probability of a declared second year student? That is, you just read that off. That's the 0.5, 0.5 for that one. The probability that you have a second year student at all, that's this one's called the prior probability, right? That is 0.6. And then what's the probability of just randomly picking a student and having them be declared, having them have a declared major? That one's a little bit more complicated. It has to do with like some interesting ideas here. So like that's this one, kind of both of those together. What are the probabilities of both of those together, right? Because everything but these, yeah. So probably both of those declared together, and the way that you can get that combined probability, like what's the probability that I have a second year student and they've declared? What's the probability that I have a third year student and they've declared? The and means you can multiply. You can multiply probability. So the probability that you have a declared second year student is, you say, 0.6 times 0.5. Does that make sense? You have a declared second year student. The probability that you have a declared third year student is 0.4 times 0.8. So the probability that you have a declared student at all is the sum of these. Does that make sense? That's how we came up with it. Okay, so that's this one down here is your 0.6 times 0.5, which is technically the top of this for a reason, right? 0.6 times 0.5 plus 0.4 times 0.8. And so those are those. It's just kind of like how much weight is there, like this one or this one, which one, like this is the one we care about. This is the only other option. It's just kind of like this over this plus this. That's the new weight. That's the new 1.0 now. That's the new 100%, because you know it's one of those. So you kind of like what's the right word? I don't even know. just like give new weights to probabilities. You rearrange the numbers. So like this plus this is now 1.0 for you, and that's what you're doing. So yeah, that's the answer, and it apparently is about 0.48. So it is more likely that it was a third year, given that you found a student that, and you know that they've declared their major, even though there are fewer third years in the class. That was how that worked. Okay, so that's Bayes' rule. So like this is probably a very good thing to be putting on your cheat sheet, something to remember and understand how to use. Okay, so I think that's what I wanted to say about that. That's pretty much the topic of the last chapter of the book. Are there any questions about that? Not so much writing code for this. I mean, you can use Python to do the calculations for you. You can do a simulation, but it's kind of easier to just understand the math, I would say. It's faster that way. So yeah, I think that's what I wanted to say. Yeah, if we're good with that, there are some other ones, other examples that like the Berkeley people used, but it's just more of the same stuff. And so I think we've covered everything. We're about at the normal time for class anyway. I think that is what I want to say. So we went over most of the things that we've ever talked about. It's wonderful. Hopefully that you found that helpful. Let me know if you have any questions about things. And then, yeah, just remember what's going to happen on the final day. You're going to come in, you're going to go to this, just like for the midterm, you're going to come here, you're going to open this, you're going to have like links to those 3 pages you can be on. I should say, here, are we here? Dun, dun, dun. Remember that when you go to this link for this online Jupyter notebook, like, make sure to very quickly copy it over to Canvas if you're ever doing something, because like this page, like if anything, if you go away from it for too long, I've noticed that it just like it stops working and it tries to reconnect. I don't know if you've experienced that before, but just keep that in mind, because like this is all ephemeral. If you close this tab, you've lost everything. So like make sure to bring it over to Canvas as often as possible as you're taking the test. But yeah, I think that's my last word of advice. So yeah, just good luck. Study hard. Let me know if you have any questions. And I think that's all I got. The rest of the time is all yours to work, study, ask questions.